Okay, so what we want to do here is we want to figure out how to calculate the area of a fence or a wall. And that fence or wall, what we want to do is we want to build it here in the XY plane. So we've got some function here in the XY plane that's just, two variables. And then we've got this green surface that's three variables. And we want to build our wall so that the base of it is touching this curve in the XY plane, and then we're going to build it to a height of however tall the surface is above this arc. Let's go take a look at that in a little more dynamic way here. So here's the graph. This is the graph of the green surface, and this is the red vector valued function just in the XY plane. Okay, so I want to build this wall like this. So it's going to be shorter over here. The wall's not going to be very tall over here, but then as I move this way, the wall's going to be taller and taller. Okay, and it's going to create some area. I mean, I think you've got it visualized. We could try to draw it, but it's probably not going to be super pretty over here, but until it touches the surface, right? That's going to go underneath there somewhere. And you could think about how this wall would intersect this green thing here. It's not going to be, it's going to be like at different elevations. Well, we saw that in the other part. It's going to be different elevations where it was not as tall here and then taller here. So that's our charge. How do I find the area of this two-dimensional wall or curtain or fence, however you want to think about it? Okay, so that's our motivation. Let's see if we can develop some theory that will allow us to figure that out. All right, so let's look at this like we're looking directly at our wall. And this red curve here is going to represent the curve in the XY plane. And then this green curve is going to represent, the top of the wall where it was intersecting that equation in three variables in our surface. Okay, so the idea here is we're going to, just like we did with areas before, we're going to partition it into rectangles. We're going to partition um, our curve here that's lying in the XY plane. And then we can pick some random rectangle here, and we can figure out how to calculate the area of that rectangle. All right, so the area of that rectangle is going to be length times width. So how are we going to talk about this little piece here? So that's some part of our partition. And is it a dx? We've done this before where we've cut this up into delta x, delta y, delta z. It's really none of those things because in this picture it would be, some little piece here along the curve. It's affected by both x and y. So I don't know if you remember, but when we did integrals that calculated the length of an arc, we called that S, the length of the arc S. So we're going to call this little distance right here ds for a tiny bit of arc length. I think we've used that recently, so that should be okay. Okay, so now what is the height of this rectangle? So what we want to do is we want to pick some, rando point in here. Now if I pick this rando point, that's going to be some point in the x sub I, y sub I. Now I'm using the same subscript there because my partition is only going to be on this one-dimensional thing. So let's say I'm starting my partition right here, then this is the first interval, and so if I picked some point in there, it would be from the first interval, so I would call it x1, y1. And if I picked some point in here, it would be from the second interval, and I called it x2, y2. When we did partitioning like areas, we could partition x into n pieces and partition y into m pieces, right? They didn't have to be equal. So when we picked some point in an area, we had to subscript them differently, x sub I, y sub j, because it could be different different values, okay? But these are all the same, so they're going to have the same subscript. Okay, so I'm going to pick some, let's say I have a point in this interval, x sub I, y sub I, and we could put some star, some notation, might call it a star. So what is the height of the rectangle at that point. Okay, so this function, this green function, is a function of x and y, right? And it has an output of z. So therefore, the height of this is f of x sub I star y sub I star. That's the height. Okay, so I think we've got the height and the width of our rectangle. Now we can calculate the area of the ith rectangle. You got it? Right, it's going to be the width times the height. So the height is whatever the value of the function is for some randomly chosen point in that interval multiplied by the width of the rectangle. That's approximately. Okay, so now all I'd want to do to find my total area, to approximate my total area, is add all those up. So I'm going to take the sum from I equals 1 to n of all these rectangles. See where we're going here. Looking good. So now I need to let n approach infinity to get the exact area. And then we can write that as an integral. Gotta move the cat before it does something with my video. The integral of f of x y ds. Now our bounds are going to be, you know, say this is some value a and this is some value b, and we'll talk a little bit more about those values here in a minute. Okay, so there's some, this looks great. We're like, oh, we got a formula. This is wonderful. But we've got some issues here. First of all, we've got ds, where s is an arc length. So, and then we have this function in terms of x and y. That's going to be a problem. How am I going to integrate this with respect to the arc length when my function is in terms of x and y? And then I've got these bounds from a to b on this red curve, but this red curve, you know, could have two variables in it. Is a and b from the arc length? You know, we've got some issues here. But it's a good start. So what we need to do now is we need to deal with this ds business, okay? We're not really going to be able to evaluate this integral the way that it's written. Hopefully you can see that, because this is going to be in terms of x and y, like I said. Okay, so we're going to go do some work, and we'll come back to this, because this is good work. We're going to just modify this a little bit after we do some stuff. So let's look at ds. So what I want to do is take a picture like this and just kind of blow it up a little bit. I'm going to write my S curve a little bit differently so it has some more slope to it. So let's say this was my curve and this is my partition and this is my ds. So some little tiny piece of arc length. Okay, so I could draw a rectangle here. Remember, this is some function here in the xy plane. So this would be a small change in x, and this would be a small change in y. Right? Because my functions in terms of x and y and s is arc length. So from that picture, it's pretty easy to use the Pythagorean theorem, and I can see that the small change in x squared plus the small change in y squared is going to give me the small change in the arc length squared. Okay, that seems interesting. I could solve for ds, and I get the square root of dx squared plus dy squared equals ds. Well, that's interesting. I mean, I have this ds here, I have this ds. Could I just substitute all this square root business? That's a little weird, right? I mean, it looks promising because it's got the dx's and the dy's, which is what I kind of need here for a function in terms of x and y, but the square root and the squared is not quite what I want. So let's see, what else could we do here? Let's think about, this is a bit of a jump, but go with me. What if I could write this curve right here as a vector valued function? What if I could write that as a vector valued function? Right? We've done that before. So if I did that, then the x component would be some function of t, and the y component would be some function of t. What if I could do that? Let's see. Let's go down this road a little bit. So now this red business is, maybe I should write that in red since it's going to be represent that vector valued function. Does this look like anything to you? Maybe think about that. What could we do? What could we do to this vector valued function to get something that sort of looks like dx squared plus dy squared? Maybe think about that a little bit. Okay, so what we're going to do first is we are going to take the derivative of both sides of this, or just take the derivative. What's the derivative of this vector valued function? Well, it's pretty easy, right? It's just the derivative of this first thing with respect to t, and the derivative of the second thing with respect to t. So that's going to be dx dt dy dt. Okay. Now, what's the magnitude? So this is the velocity, right? It gives you the speed and the direction. But if I just want the speed, if I just want the speed of this thing, did I say velocity? If I just want the speed, I want the magnitude of that. So the magnitude of that would be dx dt squared plus dy dt squared. Well, that's interesting. That's starting to look like this. Starting to look like that. All right, let's see. If I factor out a dt squared, I could just have this square root business. Let's see what that looks like. So if I do this, and I could factor out 1 over t, right? Because that'd be dt squared, take the square root of it, and then I'd be left with dx squared plus dy squared. That's what I have up here for ds. Okay, so if I multiply both sides by dt, let me write it. Let me write this first. I'd have the magnitude of the derivative at t dt equals the square root of all this stuff, which is ds. Maybe I could use that for my ds. Now that's interesting because if I use this for my ds over here, then I'm going to have a dt. So if I could somehow write this integral in terms of t, then I could just do the integral with respect to t. Now that might be easier than doing the integral with respect to arc length. Matter of fact, it will definitely be easier. So let's think about that. Let's see if we can rewrite this. So now I'd have a equals the integral from a to b, and we'll talk about what that is for a minute, of f of, now if I wanted to write this all in terms of t, instead of x, I would write this as x of t. So what I'm thinking of now is I'm thinking that this is going to be some vector valued function. So if I want to look at a point, say if I'm at x1, y1, what I really want to know is what value of t will get me to x1, y1. And then I can just write the height of this rectangle as f of whatever the x value of that t is and the y value of whatever that t is. Okay, so I can do this. And then instead of ds, I can say, well, at that particular t, I'm just going to take the derivative of the red function in the xy plane, evaluate that at t, and then I have dt. Okay, that looks pretty good. Now let's think about what this a and b are representing. Since we're doing our integral with respect to t, these are really times, right? So this is some time a, and this is some time b. If time is my parameter. So in other words, when I get to this a point right here, there's going to be some t value, right? Some t value that gets me to that a, and some t value that gets me to that b. We'll call it t sub 1, t sub 2. So this a and b now are not x's and y's. It wouldn't make sense for them to be x's and y's because this is going to be like some a, well actually for our picture, this is our a value here, and this is our b value here. So those aren't going to be just x or just y. if I thought of this in terms of x and y, then this point B would be, let's see, is that my x? Yeah, 2, 0. I can't have that as the upper bound of my integral, right? So what I want to put in here is what value of t gets me to the point 2, 0 in my parametric equation, and then that's going to work. Okay, so we're going to actually, in the next video, we're going to find the area of this curtain here that we use to motivate this discussion, and we are going to use this lovely formula to do it right here. All right, so we will do that next.